between the genset and the PV systems so that we can leverage the full fuel saving potential of solar. So what you see on the screen are the major components of a PV diesel hybrid system, and we'll see later how these are connected together to form a functioning unit. Alright, so where can PV diesel hybrid be used? There are some preconditions. You cannot use them for all applications. Some preconditions are that the DG sets should be used at least 3 to 4 hours per day. The load profile should be significant during the daytime. You should have sufficient rooftop space for the module installation. And the diesel fuel cost should be at least 60 rupees per liter, or roughly, more than that, to make the plant financially feasible. We prefer that the DG capacity should be more than 500 kVA so that the plant becomes economically viable. And finally, it would be great if the end customer was also looking for emission reduction or green savings. Some examples include, obviously it would be a great application for off-grid solutions or places where the grid is very weak or unstable. Like we know a number of states in India, right, where the grid is either non-existent or a grid power is available only 7 or 8 hours a day. So this could be a good application there. This application would make sense in remote industries like mining, oil and gas, desalination, etc. We are getting queries from tourist-related facilities like hotels and resorts, and it would be a good fit for places with large rooftop areas, for example, factories, warehouses, manufacturing plants, cement plants, and so on. Alright, so what does the basic setup look like? What you see on the right of the page is what is the existing electrical system at your customer's end. So you have the load, and you have maybe one or multiple DG sets supplying power to the load, and then you have the controller units for each of the DG sets. So keep in mind that this is the existing electrical system, and we are not going to touch it at all. It is going to function as it is, except for fuel saving. So what we are going to do is just add solar to the mix, but we are not going to fiddle around with the DG sets in any way at all. So if you see at the bottom, your DG set will have an engine and it will have a generator. And the power coming out of the generator will be flowing to the load. Now, the engine and the generator are both exchanging information with what we call the controller. So your frequency and your voltage data, that is being captured by the controller. So we can say that the controller is the genset head, and that is the interface with which our PV system is going to interact with. Let's take an example where you want to install PV which is lesser than 20% of the total genset capacity. That is fairly easy to do. You do not require anything special to synchronize them. You just add the output of the PV to the load bus bars, and that's pretty much it. However, if you want to go to higher PV penetration, and if you want to have say up to 60% PV which is 60% of the genset capacity, then you need SMA's fuel safe controller, because otherwise there will be too much, the system will be too dynamic, and you require these boxes which are intelligent. You require these microcontroller fitted boxes to help ensure that your system is running smoothly and takes care of the load in all circumstances. One very important thing to note here is that people are often concerned that the fuel safe controller will interrupt the gensets, or it may harm the gensets. We should realize that this is a total misconception. The fuel safe controller does not control the genset at all. It is only controlling the PV power, keeping in mind the load requirement at any given point of time. And I'll explain in further detail why I am saying this. So as you can see here, basically you have the genset which is supplying load, and the PV is also connected at this point. So considering the load requirement at any point, the FSC is directing the PV to increase or decrease the power as needed. So as you can see, we are not controlling the genset in any way. The only thing we are doing is we are taking one-way communication data from the genset. That's all. Another way to look at it is that the PV is acting as a negative load, right? So when the PV is supplying power to the load, the genset sees that the load has become reduced. So it automatically decreases its capacity. So that's another way of looking at it. All right. So just to give you an example, an idea of the market conditions that exist. Dr. Sanjay talked about this earlier, so I'm not going to spend much time here. But this is a global study which shows that approximately 48 gigawatt of diesel gensets were installed in 2011, and out of that around 23 gigawatt was for base load conditions, and that is where our PV hybrid solution would make the most sense. So we are talking about this 20 gigawatt or 23 gigawatt installation which is added every year. So if we capture just 1%, you can imagine how much scope there is for diesel and solar hybrid solutions. And apart from this 20 gigawatt added every year, we also have this 300 gigawatt which has already been installed in the past, and where we can retrofit the PV diesel hybrid application. Excuse me. So I'll be using this PV diesel hybrid and fuel safe controller alternately, interchangeably. Both mean the same thing for us. I think all of you guys are aware, since you are connected to the solar industry in some way, that solar energy costs have come down drastically in the last 3 years, more than 50% actually, whereas the costs for diesel gensets, or rather the costs for diesel fuel, is increasing every year. I mean, we all are aware, right, that every 15 days we hear on the news channels that diesel prices went up again for one reason or the other, whether it is a war in the Middle East or some political situation someplace else. We know that there is high volatility in the in fuel prices, and it is increasing. It's not. I personally don't think it is going to come down anytime soon. So, which means that our estimates show that energy from solar systems is already significantly cheaper than energy from diesel gensets. Estimates show that energy from diesel gensets could cost you anywhere from 14 to 18 rupees, depending on, you know, location, transportation costs, and so on. Whereas solar energy is already much cheaper than this figure. And this gap that you see, we are expecting this to become even bigger in the future. So solar PV, solar already makes sense if you compare it to DG sets. Alright, so this chart shows a comparison. It actually shows where, in what areas would diesel hybrid systems be most feasible. For the ideal situation, you should have, so this is the payback time, right? And we are assuming that, say, a payback time of 6 years or lower would be attractive to customers. So to have a payback time of 6 years or lower, you need to have a diesel cost of roughly $1 per liter, which is already the condition in our case in India, because I think diesel costs are hovering around 55-60 rupees, if I'm not wrong. Yeah. So India is already meeting that condition, and your radiation should be somewhere close to, or rather more than 1500 to 1500 kilowatt hours per kilowatt peak. As you can see in India, rough average would be 1800 kilowatt hours per kilowatt peak, or sorry, 1500, and which tells us that in India we would get an average payback time of 6 years, maybe lesser or maybe slightly more in some cases, depending on the location, radiation, and so on. So India is a fit case for hybridization of PV with diesel. All right. So now, what are the cost factors involved? So as you can see, you have the gensets for which you've already paid the fixed cost, and then for the extra power, if you have a pure genset, then you'll have these fuel costs year over year. Whereas if you put a PV diesel hybrid, then yes, you'll have high capex in the first year, but you'll have reduced fuel consumption year over year. And when you do the math and you do the comparison, you'll see that the payback time will come to around 4.5 years in this particular case. This is how the payback would come about. If you want to refine your calculation and make it even more realistic, if you want to make your calculation more realistic, let's assume that the fuel costs are increasing 5% every year, which is, I think, actually a conservative estimate. And for the PV diesel hybrid, you have the capex cost in the first year, but you also have the interest repayment on the debt in the first few years. So then the more realistic calculation for your payback time. In this case, it is coming to around 5.5 years. All right, so we did a financial calculation for a 2 megawatt system. We assumed 1600 kilowatt hour per kilowatt peak per annum. We assumed a PV system cost of around 1 lakh per kilowatt, and effective fuel cost of 70 rupees per liter, including transportation costs. And this is what we got. We got that the break even would happen after 4 to 5 years. We have the tools, we have the financial spreadsheet with which we can help you do this financial analysis for any proposed system that you might have. So you can feel free to contact us with the details, and we can help you do this scenario. Okay, now let's talk about a question which many people have raised and which many people feel is an obstacle or a bottleneck to PV diesel hybrid systems. And the question is this, that if the genset is operating at a lower capacity, say 50-60% capacity, whatever, then its efficiency goes down, which means that there is no fuel saving. I'm not saying that. This is the question which is phrased by a number of people who are new to this field. So the first part is correct, but the second assumption is wrong, and let's see why this is the case. So if you can follow the green triangles, right? So this is for a particular inverter we have chosen, diesel genset brand we have chosen, and you can see that the efficiency of this genset would be slightly lesser than 15 units per gallon. And instead, now this genset was working at 30% load, 300 kilowatt. So this is a 1 MVA system, a 1 MVA genset. And now if it was operating at 300 kilowatt, 300 kVA, then its efficiency would be lesser than 13, or rather 13 close to 13.5 kilowatt hours per gallon. So earlier it was 15, now it is 13.5. So what we see is that there is a drop of 10 to 15% in the fuel efficiency of the generator when it goes from 100% utilization to say 30% utilization. And we do not expect that the DG set would go below 30% because our fuel safe controller does not allow that, and the controller, the GCU itself would not allow that. So there is only a loss of 10 to 15% in generator efficiency. What that means is that let's assume your generator was consuming 100 liters at 1 MVA. Just, I'm just making up numbers here. So at 1 MVA it is consuming 100 liters. At 300 kVA, it would consume roughly 35 liters. That's what our calculation shows. Instead of 30 liters, because of the reduced efficiency, it would actually consume 35 liters because there is a 15% drop in efficiency. So you are still saving 65 liters of fuel, and I think that is a significant amount, right? So it makes absolute sense for us to run this genset at a lower efficiency, at a lower capacity, and supplement the remaining power with PV. So you can say it in another language that it is more economic not to produce the full capacity from the genset and instead run it at lower loads. Okay, so now we want to show you some single line diagrams of what a system would look like and how it would behave in real life conditions. Okay, so the time is around, so it is midnight right now. As you can see in this graph, it is around 2 p.m. at night, right? So the sun is sleeping, you do not have any solar power, and your load is also low, it is only 100 kilowatt. By the way, this 100 kilowatt is real-time power, and 1000 kilowatt is the maximum capacity. Similarly, here, this is the real-time output, 100 kilowatt, and 400 kilowatt is the maximum capacity of this genset. For the second genset, 0 kilowatt is its output right now, and 400 kilowatt is its rated capacity. Same is the case with DG number 3. zero output right now and 400 kilowatt maximum capacity. And along with this, you are complementing this with a 800 kilowatts PV system which is giving you 0 kilowatt right now because the system is sleeping. Okay, now let's flash forward to 9 o'clock in the morning. So the time is 9 o'clock, the sun has woken up and your system is giving you 200 kilowatt. And now your load has also increased to 800 kilowatt. So what happens? Your GCU will essentially make sure that the load is divided between the two gensets and you'll end up getting 300 kilowatt from DG1 and DG2. Now, as the sun continues to rise further in the horizon, it's 11 o'clock and you have much more radiation and your solar system is giving you 560 kilowatt. Because of this, the DG sets see a lower apparent load and they will only give you 120 kilowatt, and this is where your fuel saving is coming in. Now let's assume that one generator tries to shut down because it thinks that, you know, I'll take care of the load entirely by myself. If that starts to happen, our system will give an alarm and it will make sure that there is sufficient spinning reserve present in the generators available to take care of the load in any situation. And by any situation I mean that the solar suddenly goes out or clouds come in or so on. So what happens? Suppose one DG set shuts down and only one DG is available. What our system will do is, as you can see earlier, the PV was giving you 560 kilowatt, right? Now what happens? Now in this case, the PV reduces its power to 420 kilowatt, and the output of so that the output of one DG rises, so that the system is forced to activate both DG sets at the same time. And this is what we were looking for. We want that the spinning reserve of the generators running, whether it is 1 DG or 2 DG, should be enough to take care of the entire load. In the first case, since only one genset was running, the spinning reserve was not enough because the total capacity of the genset was only 400 kilowatt. So our objective here was to make sure that both gensets are running in tandem. Okay, so now we are at 1 o'clock in the afternoon. Now we are at 4 p.m. in the evening, and the solar PV output has reduced to 200 kilowatt. Therefore, since now your load is 950 kilowatt, so you have 750 kilowatt which needs to be
Piyush, just to interrupt 1 minute, because there are only 5 minutes left. The whole session is 70 minutes, and it will automatically stop. So I request you to, wind up and take few questions.
Okay, sure. Okay. So I think the principle is makes sense here.
complete at least presentation in 5 minutes.
Sure. All right. So as you can see, as the solar is reducing, the DG sets take up the rest of the load, and obviously at night the DG sets are taking up the entire load. This is a real life example of a cotton mill in Tamil Nadu where SMA installed a 1 megawatt system, and the modules were installed on the roof of the factory, as well as some modules were installed on the ground also. These are the details of the project. There was a 1.25 MVA genset, and it was upgraded with 1 megawatt of solar along with the fuel safe controller. This is another example at a mining site in South Africa. And this is the single line diagram for yet another project that we did in Tamil Nadu. You can see there are two DG sets which were synchronized together. We have solar PV, we have the fuel safe controller, we have the interface module which tracks the inverters, and we have the data acquisition module which tracks the load. And we also have, in this we also have a provision to feed the extra power to the grid. During the day, for example, if the PV is extra, which is not needed by the load, we can also feed that into the grid because there's a bidirectional meter available here. All right, just to recap, if you want up to 60% penetration of solar, you obviously need the fuel safe controller. And that's it on my side. Any questions?
Yeah, Piyush, I will just read out few questions.
Okay.
We have received question that if we don't have any backup, is there any controller or any settings in the inverter that will limit the uses of DG up to 30%? This is asked by Sikta Suchishmita.
No, sorry, could you repeat that? I don't understand the term backup. By backup, do you mean like batteries?
You have taken that.
Sorry, could you repeat the question?
I will read another question.
Okay.
This is Nupur Solanki. He has asked, is there any problem to DG set if your operation of PV is higher than load? If yes, then what happens to the generator? I think you have addressed that.
Yeah.
Then let me read out some other questions which are received.
Okay.
So if system where is more than 20% and less than 60% of DG capacity, how do we decide that whether to go for controller or not and borrow such? How much will be the fuel saving?
Correct. So fuel saving we can calculate once we have the specifications of the project.
I will request all the participants that we have received most of the questions, and we will be putting answers to your questions on our blog as a part of the presentation. Because of shortage of time, I may not be able to take all the questions, but we appreciate your participation, and you have our email address, and please send us email at sanjay@firstgreen.co. And For Piyush, I will also send you the email address so that you can ask your question to him as well directly.
Sure. No, we will be happy to answer any questions, queries, concerns.
So thanks participants a lot. We had a wonderful participation, and we were still having 58 participants as on date, as on time. We, depending on the further request, we may like to repeat it because there were about 125 participants. We could not accommodate all because of the limitation of our hosting package. If required, we receive more requests and we will rehost it, and the presentation slides will be available and the video will be posted on our website. Thank you a lot.
Thank you.
Thanks, Piyush.
Yeah, okay. Thank you, Dr. Vashish.
Bye.